All right, so as I promised, I want to talk about this article, semantic parsing on freebase. Freebase, I think 15K, for example, the smallest one, from question answer pairs. So what are propositional logic? What is predicate logic? I think predicate logic is just the extension of propositional logic. So instead of sentences that we use in propositional logic, I mean, the first citizen is a sentence in propositional logic. But the first citizen is object in predicate logic, like graph knowledge graph. And so you can see it is the extension of that. The general thing is higher order, and then we have predicate calculus, which is extension of propositional calculus, and this is very old, P then Q and those things. And the annotated logical forms, it's very expensive to just hire some people for annotation. If you have lots of things to do, such as, for example, saying an unlabeled utterance, like most recent parsing papers, you could say, so which one has highest probability? Paper whose key phrase is parsing, let's say 20%. Papers whose key phrase is parsing and has the largest publication year, yeah, this is nice, maybe 60%. Number of papers whose, we are not talking about the number of papers, we just want the papers. So maybe 20% for this. And so the crowd workers, I mean these cheap, very cheap labor market, unfortunately they have to do all of the things and create some labels for us. And then we train using all aggregated information. So we convert this to some grammar output, because it's very ambiguous if I say, give me most recent parsing papers. The machine doesn't understand. What do you mean? Most recent parsing papers? I understand because my database is like this. I'm talking like a robot. So the paper whose key phrase is parsing, I understand it. Paper whose key phrase is parsing and that has the largest parser, I can take the maximum. So I have learned this. So I learned this. So I know this one. Another sentence, I also understand this sentence as a robot. So the number of paper whose key phrase is parsing, because I can count. I'm a robot, I can count. But if you give me most recent parsing paper, I don't understand it, which it's very romantic, it's very literal. It's like a person from a very complex background. I don't understand it. But this is like a machine. I can count, I can add, I can take the maximum. I can count, for example, I have a knowledge graph. I can count all of these edges and say, okay, the answer is 4. And in 2013, a nice paper, we understood that we don't need for annotated logical forms. And I will explain this article from Percy Leung. And so the problem is, given a knowledge base, your knowledge graph, and a training set of question-answer pairs, output a semantic parser that maps new questions to answers via latent logical forms Z and the knowledge base K. So still we have X and Y. This is sentence, this is sentence. But we have, there is a Z as well, that latent logical form. So we don't know this. We want to infer that. So like variational autoencoder. No, not like that. Like, for example, just general deep learning. You have some input and some output. And, for example, after the convolutions, you have some implicit nice features that are good for representation. Or any other feature, any other implicit, for example, hidden Markov model, anything that is hidden. Or like semantic hashing that you represent it with, for example, you have autoencoder here. In semantic hashing, we represent it with some discrete vectors such as 1 0 0 1 0. So this is the latent one. We don't know this Z, and then after you give it to the decoder, you get the same thing. So Z is implicit. And here Z is a logical form. We don't know it, that logical form. So semantic parsing on freebase. So instead of relying on annotated logical forms, we try to avoid those labels in supervised learning, which is very expensive. You could get it, give it to crowdsourcing guys, and it's so expensive. Each hundreds of dollars per person per minute, and so instead of that, let's have a creative idea. The main challenge is narrowing down the huge number of possible logical predicates. For example, when we say, which college did Obama go to? Here we execute it on database. If we can say, okay, this is the type of the university, and if we end it with education of Barack Obama, we can execute it on a database. But this form Z is hidden. We don't know how to create it. So we build a coarse mapping from phrases to predicates using a knowledge base and large text corpus. And then we use these bridging operation. For example, here education is a bridge. We didn't talk about this education. We just said college, but it is related to education. So it's a bridging in order to understand what part of database which table we need to focus on. And at the lexical level, a major challenge in semantic parsing is mapping natural language phrases. For example, attend to logical predicates such as this bridging word, which is education. And so for that, they use Lambda DCS. I will explain it in next lecture by Percy Leung. He has invented it in a short paper, maybe 10 pages, but it's just a new form of Lambda calculus, a simplified version of that. It's very simple. That we try to reduce the complexity of your Lambda calculus, and then here introduce unary base case, binary join, and all those things in his article that I will explain in the next lecture. And of course, we have intersection and aggregation as well in this article. But the framework that we are talking about is like this. So this is the thing that we want to do. We don't know this type, that location, all of these dependencies. So this is semantic parsing. It's different from dependency parsing, which is more syntactic, more linguistic. But here is more semantic, more meaningful thing, like semantic web, like semantic parsing. And for each derivation, D here is a tree, which specifies the application of a set of combination rules. And we have composition. I mean, derivations are, for example, this is one derivation. This is just one derivation. We don't know which derivation is better. Just like dependency parsing that I will explain. You could have different dependency structure on the grammar, on the sentence, on the words of the sentence. But one of them is more probable. That's why we give it we separate the sentence, or we can do very interesting things for that. And so this is the composition. And for example, intersection is Z1, Z2, join, aggregation Z1, Z2, bridging Z1, Z2. And we want to maximize this objective function. So what is the probability of a derivation given your x? Look, x is just a sentence. So you give x to our model. It gives you, for example, with this probability, D1 is good. For example, we have softmax. With this probability, D2 is possible for the answer, and so on. For example, we have M classes. And we just maximize this as usual, nothing strange. So we use this log linear model. You see, this log linear model comes from discriminative models. You have two types of models in machine learning. Generative model. So let's say generative model, like for example, P of X, Y. It's hard because you should know all of the probability. But we know from the interview of Lex Fridman with the father of machine learning, Vladimir Vapnik, that if you have a very big question, you don't need to solve big general questions. Just solve the necessary and the things that you need it. For example, here, if we use discriminative analysis, we just need this conditional probability Px given y. You don't need to go through Bayes rules and those things to calculate Px given y, Py divided by Px, and even you fall in the problem of your denominator is intractable, so you should go and find, for example, a Markov chain to approximate this Monte Carlo Markov chain. But if you just use this discriminative analysis, discriminative model, you just need the conditional probability. We all know those beautiful softmax can do anything. And that's why these like linear models, you can see it in almost all problems of supervised learning in machine learning. And there are two strategies for generating a set of meaningful a manageable set of predicates. So our knowledge base has more than 19,000 properties. And so a major challenge is generating a manageable set of predicates for an utterance. Utterance, for example, your expression, your sentence. This is your utterance. So we propose two strategies for doing this. The strategy one, we construct a lexicon that maps natural language phrases to logical predicates by aligning along large text corpus. So you see an example. First of all, it is typed in what was that Facebook, freebase. Freebase, it is typed. It means that each one has a type. For example, this is person and location. A person grew up in some location. A person is born in some date. A person is married in some date. A person is born in some location. Of course, we do some lemmatization because there is some ambiguities. For example, born in, it could be place or it could be date. So that's why we do some we do this in order to, because the type helps us to remove this ambiguity. And maybe this was the motivation for freebase. I don't know. And the alignment, so as I said, we want to map phrases to predicates. The things that your database understands: place of birth, marriage, from the table marriage, the column is start date. For example, you have a column, we have a table place lived, you have a column location. For example, your traditional SQL databases, it's very easy. Even in graph-based databases like Neo4j. And we translate it, but we don't know how to do that. But the simplest thing is that we just word by word. Grew up in is more probable to marriage start date or something like this. But it is very noisy because sometimes we notice that 4 occurrences appeared for borning and marriage end date. Maybe because both of them is related to date. So if we just follow the first strategy, we are failed. I mean, we are not failed. We can just handle some of the ambiguities, but the remaining ambiguities still remains. So what? What can we do? So for a phrase born in, L of W is a set of entries. Z is a predicate, S set of features. And the features for alignment is feature 1 is this, for feature 2, feature 3, feature 4. So we have 4 features. The first feature is log of number of entity pairs that occur with the phrase, for example, born in. The other feature is log number of entity pairs that occur with the logical predicate R2. For example, date of birth. And feature 3 is interesting because it joins them. It joins 2 different types. 2 different things. The sentence and the word and the things that the grammar, the things that the database understands. The semantic meaning, I mean. And the last feature is also interesting. Whether R2 is the best match for R1. And so for alignment, even for word to word, we have 4 features. So 4 features. As I said, alignment is not enough. Still, we have some ambiguities. Of course, this is the way that this paper is working on these features, interesting features. So some of the ambiguity is removed by these alignment techniques, some of them by lexicalized, some of them just text similarity is enough. But when it becomes more complex, the ambiguity, when the ambiguity is really high, then we go to look at bridging technique and even composition, which is the highest. Bridging has more ambiguity, and then maybe composition, and then text. Lexicalize, and then text similarity, and then alignment. So alignment is the simplest way that comes to the mind, because there is very obvious way to do that. Alignment features are unlexicalized and measure association based on argument overlap. Lexicalized features are standard conjunctions of the phrase W and the logical forms Z that we want to infer. We don't know the logical form. So in lexicalized features, it's just conjunction. And the text similarity compares the untyped phrase, for example,